Okay, our next presentation is Can New Drilling Technology Uncover the Next Generation of Deposits? It's by Richard Hillis, the CEO of Targeting Deep Exploration Technologies from the DTCRC.
Thanks very much. Okay, thanks very much. I've got some different introductory slides. Terrific that Cam and Roger covered the cover issue. My introductory slides are slightly different, but I think another important part of the context. Some of you may have seen this slide, but you may not all have seen it. The amazing statistic that between 1981 and 2005, the world mined as much copper, used as much copper as it had ever previously used in history. Amazing. What's even more amazing is that it's on target, GFC notwithstanding, to repeat that feat from 2005 to 2030. So the area under this curve is the same as the area under those two. So over two 25-year periods, we have used as much copper as we've ever previously used in history. And that is drawing down the reserve. These are Rio Tinto data. You can take whichever data you like. In the face of this amazing drawdown, let's say Rio's data, 1996, 45 years of reserves at 1%, 2008, 25 years at 0.7%. And of course, part of this challenge, part of our failure to replace the reserve, is the challenge of exploration under cover, our lower success rates under deep masking cover. And just a couple more of these slides before I get into what I think the new technologies are that may transform this. Here's a slide of Richard Shoddy's of discoveries against exploration spend. So 1950 through to 2010, the background green is exploration spend, the blue is discoveries, and of course, broadly we spend more, broadly we discover more, broadly we spend more, broadly we discover more, and then this last period of expenditure with much poorer return. Now, Richard himself admits that some of these conversions may yet go in, and it may look a little better, but it's going to look worse than these last two. The challenge is getting harder. Do we need a new approach? Gold doesn't look a lot different. So gold expenditure, gold discoveries, and I enjoyed being at Roundup a couple of weeks ago, and Pierre Lassonde gave that data. So those supergiant golds, or whatever you call 20 million ounces, 14 discoveries in the 80s, 11 discoveries in the 90s, 5 in the noughties, and none since 2010. So there's a pretty clear and strong trend there. And a bunch of companies got together and said, look, this is a major challenge. And we need a consortium, as well as all the geology and the footprints, we need a consortium to change the way particularly that we drill. Because with all due respect to our drilling, 120, 130 years ago, the Boyles brothers bought a diamond drill, drilled holes in the western US, and acid core for copper. It is a remarkably, all right, we've got wireline core recovery, okay, we've got RC, but it is a remarkably unchanged industry. So these are the sponsors of an organization called the Deep Exploration Technologies, CRC. And there are, in fact, about 40 CRCs in Australia. They cover Aboriginal health, cancer, motor cars, and in our case, mineral exploration. They have in common that they are half funded by the federal government and half funded by industry. And the federal government basically says, we'll leverage that money provided it's an industry-led agenda, provided it's not an academic or esoteric, provided you're going to produce industry outcomes. So that's our concern. We also have a bunch of affiliates, and we have a particular engagement with the service sector because we will commercialize our IP through the existing service sector. So we have geological surveys involved. These are all service companies and also a few junior explorers. I think I've probably covered that. For your interest, we're spending $120 million on research on new exploration technologies over the period 2011 to 2018. So it is a significant effort. We fund about 120 researchers in various places. 3 programs, drilling, logging, and targeting, and Cam had that fantastic slide where in 1961 the Gulf of Mexico had 1 day of oil reserves. The world uses 85 million barrels a day. So in 1961, there was 1 day of oil reserves in the Gulf of Mexico. And then, of course, all that new technology came on. And the technology was seismic for targeting. The technology was logging while drilling. The technology was the ability to drill in deep water, like riserless drilling. So, not surprisingly, we end up with targeting, logging, and sensing and drilling. And I'm not going to, in a catalogue way, go through them all. There isn't time, but I'll try and give you some highlights from each of those areas and how we think they can be transformational for the way we explore. So our flagship project is to turn the drilling rig you know into something like this. This is a coiled tubing rig, and you can read for yourself the stats up there on coiled tubing. They are stunning. Coiled tubing rigs can drill 2 1-kilometre wells because it's a petroleum side, wells per day. 2 1-kilometre wells per day. No connections. So you're not making any connections. The drill string is on a coil. You're not making any connections. So you can trip in and out to 1,000 metre in minutes, an hour to replace a bit at 1,000 metres. You've got no manual handling of rods. It's also environmentally very clean. So a lot of advantages. There are challenges as well, of course. If there weren't challenges, everyone would have done it. What we're targeting is a coiled tubing rig that weighs less than 10 tonnes. Conventional rigs are about 40 tonnes, just road legal in Australia. We'll drill for $50 a metre to 500 metres. That's our initial challenge. And there are some key challenges. Coiled tubing drills those incredibly fast wells in relatively soft rocks. It's used in coal seam gas. So can we get coiled tubing drilling to drill harder rocks? What that is going to mean is a much faster spinning motor. You've got a downhole motor and a much faster spinning bit, thousands of RPM, not tens of RPM, and a very precise control system, because it's going to have to advance at perhaps 1 millimetre per few seconds so that the depth of cut is very precisely monitored. We also have to get the coil, the steel coil, or perhaps composite coil on the tubing, more resistant to becoming fatigued. Currently, we're getting about 10 to 100 winds or unwinds off of coiled tubing. We need to get that up to 100 consistently, and then it becomes cost-effective in min-X versus the typical life of drill rods. So there are real challenges in fast motors, in control systems, in tubing, and we are doing all that analysis. We have all those groups. We have, in fact, just ordered. This might be your glimpse of a rig of the future. It's quite small. This is a small coiled tubing rig, just being built for DET CRC in Houston. It hasn't got the coil on it, so this is really just our platform. This rotates back, and there's an injector here that injects the coil. We're going to put 150 to 200 metres of coil on that, and we are taking that to South Australia, where, along with the South Australian government, we have a drilling test facility that I'll talk about in a second. So that should be on a ship to Australia within weeks. And that will become our platform for precise control systems, for very high-speed motors, for testing all these things. But, you know, even if you don't solve all the problems, you've probably got something that can very easily drill through cover for pre-colors. And in fact, one thing we do know from petroleum is that coiled tubing is fantastic for stability, because you are continuously clearing the cuttings. You're not stopping to make connections, you're not turning fluids on and off, you don't have surge and swab pressures. So coiled tubing in itself is fantastic for unconsolidated cover, essentially because you're continuously clearing the cuttings. So that's one of the pieces of kit in our lab. That's the transformational project. We have a bunch of other projects that are perhaps more about making existing drilling more cost-effective. And in fact, these projects overlap, the revolution in new coiled tubing drilling and the optimizing existing drilling. But one project that has captured people's imagination is the carbon fibre drill rod. So there's a carbon fibre rod in the string, and again, that's at our facility near Adelaide. If we just zoom in under the driller's platform, you can see it's actually there. And I'll just go there. Let's see if this little bit of video will play. Yep, just to convince you it's actually drilling. So that's the world's first minerals drilling with a carbon fibre drill rod. It's not drilling very fast, but it does go down. Well, we actually did that just before the South Australian Premier launched the facility. We said to the driller, don't go too hard before the Premier sees it. but then after the Premier's seen it, you can go as hard as you like. And he actually had a lot of trouble breaking it. In fact, we've now done a lot of testing of these carbon fibre rods on the dynamometer at Port Longyear. We're housed in with Port Longyear, and they can withstand 5 times the torque limit for threading of steel rods. So why carbon fibre? Now, I make tennis rackets and golf clubs and Dreamliners out of carbon fibre, and it's sexy, but what are the real drivers for it here? One is, of course, weight. It's about 2 to 3 times lighter than steel and about 2 to 3 times the cost. So, of course, if you're helicoptering rigs, your weight is a huge advantage, but if your drill string only weighs a third of what it did, then essentially the same rig can drill 3 times deeper. Your power in a rig is all about the hoisting capacity of the string. So if you make your string lighter, you can drill much deeper. The whole system becomes, the consumables are less, the weight of everything is less. We actually didn't start, we call that the dumb rod project, just replacing steel rods with fibre rods. Terrific. We didn't start for the lighter argument. We actually started because, and this is getting into the sensing, we started because we wanted to embed sensors in these carbon fibre rods, sensors that you can't embed in steel. And the driver here, I often get beaten up for this, is to as much as we can replace core. And I'll justify in a minute why we think that's necessary and why we think we can. But this is just a core orientation sensor sitting in a carbon fibre drill rod. So what happens is that senses real-time the deviation on the hole. And every time the core barrel comes down to be collected, every time we collect the core barrel, there's a data shuttle on that, and this speaks to the core barrel, and that information goes back up to the top of the hole. So every core pull, we can get an orientation point. Now, that's the sort of simplest thing to put in real time. Communication up the hole is a challenge. In petroleum, most real-time communication up the hole, believe it or not, is mud pulse telemetry, pluses and minuses in the mud pulse. Okay? So the wireline is actually a great communication tool. And of course, if you jump forward to coiled tubing, you can embed comms in the coiled tubing. We now have built, we've got other sensors that we can put down the hole real time. We've actually got a natural gamma working down the hole and are putting on MagSUS. So we are gradually building a suite of sensors that we can put on a sub behind the bit and recover information all the time. That would play into current diamond drilling, but of course would play into our coiled tubing rig. Sorry, I'll just go back actually. So what are our drivers for replacing core? Well, we believe if we can replace a lot of the core that you cut, firstly, there's a simple productivity gain. Instead of getting core, shipping it off to an assay lab, waiting 3 months for your assays, finding out you've got something, possibly remobilizing a rig, if you have information real time, you can make decisions real time. But it's more than that. It's actually about permitting different ways of drilling. If you're going to pass a stick of core up through a drill string, you're limited what you can put on that string. You can't put downhole, you can't really make effective annular downhole motors, or you're absolutely limiting the way you drill. So if you can replace a lot of the core, you permit quicker, faster, cheaper, safer ways of drilling. So that's one. Here's another, just to give you a flavor of another optimizing one. And this is one that's actually particularly being trialed by Newcrest at the minute as a prototype rolled out. This is now not monitoring the geology, but monitoring the rig performance real time. So we've got a bunch of sensors on this rig that's at Telfer. And this is simply, I think it's just weight on bit and pull back and some of the fluid pressures. But Newcrest can look at this as an iPad app. So Newcrest can look at that on their phone in Brisbane and see what the rig at Telfer is doing in terms of, at the minute, simply weight on bit, hold back pressure, but that real-time feedback. Again, that's V1. V2 is to put a more sophisticated measure. This is a sub that we'll put on the string that measures torque and other forces that we don't currently measure. That will also be transmitted real-time to Drilling Manager, who is then able to look at optimizing drilling performance. We can tell whether the bit is polishing or whether the bit is cutting from the response on these sensors. So there's always sort of V1, V2 with the geology sensors, with the rig monitoring sensors, gradually building up the suite of remote measurements. We test all this technology out at a place called Brukunga. I say the South Australian Government have been terrific collaborators in this project. It's a disused pyrite mine. It's got a lot of good things going for it. It's close to the city, happens to be able, we can do driller trading there as well, but of course there's mineralisation down the hole. So not only do we put carbon fibre rods in this and try and break them, we also have mineralised core that we assay and that we can compare our sensors. It's the calibration for the new sensors that we are developing, downhole sensors and at-rig sensors. So we're currently drilling our second diamond hole there, and we're going to drill a couple of RC holes too. I've got a little bit of animation. I'll look at the clock, a bit of time to show you this animation, just to try and reinforce the point about the downhole sensing. So I hope this helps convey what we're trying to do.
Project 2.2 will develop downhole sensors that can largely replace core. The project is developing a prompt gamma neutron geochemical wireline logging tool that will measure the concentration of elements. For example, copper above 0.025%. in a volume of approximately 50 centimetres radius around the borehole. The project is also developing a shuttle that will be lowered inside the drill rods and will log while being recovered when the drill rods are pulled. Initially, natural gamma radiation will be measured, subsequently other petrophysical parameters. The long-term aim of the project is to develop sensors that can be placed behind the bit, yielding logging while drilling information, including geochemistry, here illustrated by copper. In addition, recording mineralogy, here shown by chalcopyrite, and also recording an image of the borehole wall from which structural information can be obtained. Together, geochemical, mineralogical and structural information will remove or greatly reduce the need for core. All of these data are transmitted to the surface and then transmitted to an internet-based server for remote access from any location. Real-time data will permit follow-up drilling without expensive rig demobilisation and remobilisation.
Okay, so that's the vision. How's progress against the vision? Let me show you a couple of shots. So a couple of our wireline tools. This is actually the PGNA tool, copper to 0.025%. Wireline tool that fits in HQ, and we've run that and tested it and works effectively. We have in fact just manufactured a smaller tool that will go in NQ. We also have a downhole magnetic gradiometer. So again, we see real-time magnetic gradiometry as very useful to vectoring towards targets that you've just missed. This whole sense of real-time data coming through, real-time geophysics, real-time geochemistry, rig not demobilized, real-time decision drill 100 meters to the north after that first set of information. We don't actually like wireline that much. I don't actually like wireline that much. There's some technologies that we can only put in a wireline because we lose a lot of holes before we can put a wireline in, because it requires a separate mobilization. What we actually want to do is build to all our sensors being on the string. And we are progressing with that. So here are sensors on the string or in a shuttle. This is the data shuttle with one of our key researchers, Christian Dupuy. So this one isn't a wireline. It's simply pumped down by the driller. So you don't need a wireline crew, you don't need to hold the hole open, you just pump this thing down through the rods, it goes out through the bit, engages, and then logs, like a wireline log, as you pull the rods. No extra time, no extra mobilization, extra data for free. At the minute, we have gamma and mag sus on that, and we're just about to put induction on it. So that's the data shuttle. And then, of course, I've talked a little bit already about the sensors directly on the rods and the shuttle. So we have a suite from wireline to shuttle to sensors on the rod, all moving towards real-time geochemical, petrophysical, structural data. We're not reliant, this is, if you like, third. I've given you a little flavour of the drilling. Our program 2 is that downhole sensing program. And our program 3 is, if you like, above the hole targeting and also some of the geological footprints that Roger and Cam were talking about. But this is just one little slide, again from our work at Burkungan. It's an interesting slide. Call this Labbit rig. This is an index solids removal unit. And we did something really, really simple that no one's done before. The solids removal is important. If you've got a downhole motor, it has to have a clean water supply. So the solids removal is great. It cleans all the particulate material out. It permits fully contained fluid systems. But you have actually a volume of powder that for our HQ is comparable to the rock volume you cut for core. That's slightly more kerf than there is core. And what we simply did was just went to the sump. When we had the solids removal unit, we collect them from the solids removal every meter. Just collect this powder. And we analysed it with handheld PXRF, expecting a big lag, but actually getting a better result than we expected. So the blue, this is depth along the core. The blue is just the geologists logging of visual sulfides with core. The yellow is weight % sulfur. The red is weight % iron from PXRF of the powder. So that's all we've done. We just collected the powder. You can see a little bit of smearing, but it's not a great deal of smearing. And when you combine that with the petrophysical data, you combine that with knowing where the changes in mag sus density are, you can back out that smearing. So hopefully I've created a picture for you. And I guess if I was trying to leave you with a summary, although I did something else I want to say, if I leave you a summary of our technology, we're doing a lot of other stuff, but you can't go through all the stuff in a 25-minute talk. The key is transformational drilling, supported by real-time downhole sensing, real-time top-of-hole sensing, but this data going onto the cloud, and this data being accessed real-time and informing real-time decisions by this lightweight mobile rig. So that's something like our vision of the future and some view of progress towards it. We think, I just want to finish off, and I thought I'd take this talk back to the Gola Cradon and ILCGs and the sort of things perhaps people in this room are interested in. We think that will permit, that suite of technology, it's not just about making drilling 25% cheaper. We think it will permit a different approach, which we think can crack the code. So if how are ILCG holes targeted in the Gola Cradon? Really using 2 channels of data, and they were talked about earlier. They're essentially targeted on mag and grav data. So this is the Gola Cradon. That's a gravity image. Let's just blow up the white box, and you can see some subtle gravity features. I haven't put the grav in the mag. And you see many of those subtle gravity features are just tested by one hole. One hole that might cost 300,000 or 500,000. And sometimes they're successful. Oftentimes they are not successful. But they are one shot in the locker holes. We think the new technology will permit what we call prospecting drilling. You will be drilling sufficiently cheaply that you will go down with your first hole. These are about on a 5K grid. You will go down with your first hole. You will get the petrophysical signatures. You will get the geochemical signatures, the potassic alteration. And because you are drilling so much more cheaply, because you don't have to remobilize, because you have the real-time information, you will real-time drill out a grid and vector towards ore deposits. And we see that as transformational, and we think the cost structure is permissible with this new technology. So I've got 2 minutes. I think I've got time to show this animation as well. So I'll just show you. This is hot off the press. It's never been seen before. There's a couple of things I want to change, but hopefully, again, it'll give you a flavour.
The DET CRC reconnaissance drill rig and associated lab at rig and downhole analysis will enable a new style of deep regional prospecting, demonstrated here with the Gola Cradon, which includes Olympic Dam as a case study. Barren cover is up to 1 kilometre thick and is a barrier to mineral exploration. The coiled tubing drilling rig being developed by DET CRC drills rapidly and cheaply through cover and prospective rocks below. The coiled tubing rig samples cover and basement rocks that can be tested for geochemical, mineralogical and petrophysical evidence of nearby mineral systems. Lab at rig chemical and mineralogical analysis combined with downhole logging and real-time evaluation enables drilling programs to be updated while the rig is on site with significant savings in time and cost. Cheap, rapid, deep sampling will facilitate a new approach to exploration that we call deep regional prospecting. Regional target areas are prioritised based on available data, here using gravity and existing drilling. Priority areas are sampled in a systematic way, with geochemistry, mineralogy and petrophysics measured in real time at a sample density appropriate to the mineral system. The sampling program can be modified on the fly in response to results, changing priority, extending or infilling the drill pattern during a single deployment. The sampling program progressively maps the crustal scale alteration system and identifies hotspots, thus vectoring toward mineral deposits. Exploration companies have increased confidence to test expensive deep targets within the system and discover more mineral deposits.
Okay, so just an overview, and I guess in some ways repeating what I hopefully had articulated. Just to end with some conclusions, as I've gone critical here on the light. CT drilling offers a step change. Some real challenges to solve. We may be successful, we may not, but we are out there trying to deliver a step change. It has to be complemented by a suite of downhole and labbit rig technologies. A lot of those technologies can also be applied to conventional drilling to make them more cost effective. And we think that the CT drilling will permit a different approach to exploration undercover. So if you're interested, you can get more information on the web, but thank you very much.